to Francescomaria Faticanti, who is invited from ENS of Lyon, and he will do a presentation on orchestration of AI-based applications in heterogeneous and distributed computer systems, but I will leave the floor to him to present himself.
Thank you. Can you hear me? You need to turn it on. Yeah. Can you hear me now? Okay. Okay, so thank you. Sorry for the delay. And so first of all, thank you for having me here. And so today I'd like to, my talk is about basically my experience of research and what I've done so far since the end of my PhD and through my years of postdoc. So first of all, I would like to introduce a little bit my education and experience. I don't know why. So, an experience very close to it. Yes. But it's not that. Can you hear me now? Okay. 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 Cool. Turns off, so you just use this instead. Maybe it's a problem of batteries. I will take that. Okay, so now I hope it's fine. So I will start with my education experience. So basically, I got my bachelor and master degree in computer science at Sapienza, University of Rome. And then I moved to University of Trento in the north of Italy, close to the Alps, for my PhD. And after a brief period of postdoc at the Fondazione Bruno Kessler, I moved to France since January 2022, first at Iria Sofia Antipolis, working with Giovanni Neglia. And then since September 2023, I started working at the École Normale Supérieure de Lyon, working with Francesco Bronzino. And during this year, I want to highlight that I had the opportunity to work and lead some aspects of different projects, both from academia and industry, at international level and national level. So my research basically deals with modeling and optimization of application performance in networks. And in particular, my research basically is split in three main lines. The first one that I inherited by my PhD, which deal with the orchestration of microservice application at the edge of the network, for which I applied different mathematical methods like integer linear programming formulation, the study of computational complexity for the design of approximated solutions. The second line of research, I started it since my first postdoc with Giovanni at Iria Sofia Antipolis, is a network online caching, for which I applied methods that include the online optimization and learning. And the third line also is a line that I started during my postdoc with Giovanni, and is a distributed machine learning over network, for which I started to deepen my knowledge on distributed optimization methods. So now, in order to introduce my research, I would like to start with a question that is what happened when you press the play button of your favorite video streaming application. And so this is what happens. So basically, you are going to activate this graph. This is the graph of Netflix in particular, and this is the application of Netflix. And in this graph, each node represents a microservice, where a microservice is a software component that is implemented thanks to virtualization technologies like virtual machines or containerization. And each microservice is within the application graph is devoted to a specific task within the application. So the root of this application can be like the front end of your application, and then there is, for example, another microservice that is devoted to bring the content that you are requesting to your location. Another microservice devoted to adapt the resolution of the video to the quality of your connection. And for example, another microservice devoted to caching, to store the most frequently requested contents more closer to your location. So these applications basically can consist of hundreds of microservices, like the one of Netflix. And each microservice is, in order to function properly, has some requirements in terms of CPU, memory, storage, privacy also, because sometimes we don't want to deliver data outside a certain domain. And then we have some communication requirements for the communication among different microservices. We have the requirements in terms of latency and bandwidth that we need to satisfy. And these requirements basically constitute what we call the service level agreements, so are the basis for service level agreement that basically consist of the desired performance metrics that every time an application user wants to deploy its own application on an infrastructure should be provided. And these requirements, I call these requirements syntactic requirements, because if we do an analogy, when you write a sentence or a piece of code, a syntactic error is very easy to be detected. Okay, so requirements, let's say that these syntactic requirements are easy to verify whether they are satisfied or not. So where these applications are deployed, they are deployed on current networks, because nowadays the networks are not just a means of communication, but they are also a powerful tool of computation, because indeed we can exploit all the computation available on all the nodes of the networks, ranging from the cloud with infinite resource capacity to the edge of the network with heterogeneous capacity, because the idea is to exploit all the capabilities of all devices that are distributed among the network. And obviously, we have several trade-offs. For example, in the cloud, we have high latency times, but we have infinite capacity. Meanwhile, on the edge, we have low latency times, but constrained capacity. And basically, this network is an heterogeneous environment because each node has some constraints that should not be exceeded, some capacity in terms of CPU, memory, storage, and we have some constraints also for the communication among different nodes in terms of bandwidth and latency. And now the message is that, okay, we have to deploy this application over this heterogeneous network, but the deployment is challenging. Why? Because basically, okay, we don't have just one application to be deployed, but we have several applications that are requested by billions of connected devices that are requested for deployment or for just for the use of this application over the network. And since, so basically this application, they're just not video analytics, video streaming application that can be whatever, video analytics, video streaming, content caching, virtual network functions, or traffic analysis applications. And these are all developed by using the microservice architecture. Now, in order to deploy this application over the network, we have to satisfy the service level agreements. We need to respect the capacity of the infrastructure. And basically, when we are performing the deployment, we can perform the deployment depending on the specific objective that we are following. The specific objective depends on the point of view we are assuming. We can assume the users whose objective is to optimize the performance of their application of the network, or the perspective of the service providers whose objective is to maximize their revenue. So they want to deploy as many applications as possible. So the challenges here, for example, are several. The main two challenges in this context are that first of all, we have to deploy this application. And for the deployment, we have an exponential number of configuration. We have a combinatorial explosion for the possible placement of this application over the network. And once we deploy this application, we have an unpredictable sequence of requests that these applications are receiving. So my message is that, okay, this application should be orchestrated over the network. And they should
yeah, it's okay. Just you have the meeting right now? No, it's not the meeting. It's
okay. So so this application should be orchestrated because basically from one side we want to satisfy the SLA of the application, and the other we need to respect the constraint of the infrastructure. And for orchestration, I define orchestration a set of strategies that consist of, first of all, an initial deployment of application components of the network, and a management of these applications once they have been placed on the network over the time. These orchestration strategies are crucial to keep the SLAs satisfied and infrastructure capacity respected over the time. So in order to orchestrate these applications, basically we have to decide, first of all, which application component to select, where to place it among the network nodes, and when to reconfigure as the initial condition changed over the time, the initial condition both of the network and the data that these applications are receiving. So now I want to stress the message that basically an orchestration implies an optimization problem depending on the specific objective that we are looking at. And I would like to start with first example, that is the first work of mine that I've done together with Marco Savi from University of Milano Bicocca, my PhD advisors, Francesco De Pellegrini and Domenico Siracosa. And this is about orchestration of application in multi-domain networks under a certain kind of constraint that we call under locality constraint. So in this scenario, we have an infrastructure GI that is split in different domains. And basically, we are wearing the shoes of a main domain whose objective is to deploy a set of applications that have these locality constraints that represent the need of a certain microservice to be placed in a specific domain of the infrastructure. For example, this can represent like privacy reason, because we don't want to deliver this microservice outside a certain domain. Or, for example, it can represent the needs of this microservice to use a specific device placed on a certain domain. And the objective here is to find the placement of this set A on GI that minimize the cost that every time we are going to incur, every time we are going to deploy a piece of the application outside the main domain. The challenge here is that even though with this locality constraint, the problem is NP-hard, and furthermore, we have a negative result for the approximability of this problem. So we propose a heuristic solution that, despite the state of the art, since the state of the art failed, we are going to see this when dealing with this locality constraint, we propose a heuristic solution, basically, that explores the solution space in a different way, in a breadth fashion, let's say. In order to see the difference with respect to the state of the art and our solution, I will give you an example. In this example, we have 3 domains, and we are taking the perspective of the domain D1, where the deployment cost is equal to 0. Meanwhile, the deployment cost towards the external domains D2 and D3 is greater than 0. And we have 2 applications to be deployed over this infrastructure that present the same locality constraint on the first microservice, and to be deployed, both of them on the D1 domain. So the state-of-the-art solution basically is a depth-first search approach in the solution space. And it will start with the first application, will deploy one application entirely at a time. And it will start with the first microservice of the first application. Since we have a locality constraint, it will be deployed on the D1 domain. But since also this strategy is also greedy, it will deploy also the second and the third microservice, the first application in the domain with the lowest cost, that is D1. But in this way, all the resources will be saturated, all the resources of D1, without leaving any space for the first microservice of the second application that presents a locality constraint there. This will lead to an infeasible solution because we are not able to deploy all the applications. And so we propose a different way to explore the solution space in a breadth first. It means that basically we evaluate the parallel deployment of the first components of both the application at the same time, then the second and the third, and so on. So in this way, we are going to pay something in terms of cost because we are deploying some components outside the main domain, but at least this is a feasible solution. This solution, we proved experimentally that it presents a better trade-off between the feasibility, which is the percentage of instances that are solved by each solution, and the cost. Indeed, we can see that the BFS is able to solve the 42% more instances with respect to the state of the art. And this solution is also scalable because it takes just 0.30 seconds to deploy 300 microservices, which is the size of the microservice architecture that everyday Netflix and Amazon are dealing with. And we compare the solution against an optimal solution computed by a solver. And this solution is also implementation ready because this algorithm has been used for the orchestration strategies of the fog gatherers, which is a real fog platform that is being developed by the research engineers in my team when at the University of Trento. And this work also achieved the main, contribute to achieve the main objectives of the Decenter project, that is an H2020 European project. Now, what I want to highlight is that, okay, this was a continuum of my PhD. And basically, after my PhD, I started to work in machine learning, basically. And I was wondering, okay, how these machine learning models, because there was a diffuse use of machine learning models everywhere, basically. And so these applications started to use more and more machine learning models as a component of this application. Okay, so I started to work on machine learning in order to understand what are the main challenges. And these models are used for various reasons inside. They are embedded inside the applications for prediction, classification, and generative tasks. We have various examples for video analytics, for example, for caching to predict the next request that the users are going to submit to the caching system, to the video provider, for example, or the traffic monitoring, because, for example, we can use this machine learning model to infer some quality metrics from the traffic, for example. And in what follows, I will start to present two works. The first one is a work that tried to prove how machine learning models can improve the performance of this application. And the second work is a work where we can see what are the challenges with these machine learning models and what is new with embedding this machine learning model inside the applications. So the first one is a work with Giovanni about optimistic online caching. So basically, the message is that, okay, it's been proved that the use of machine learning prediction improves in network online caching. Online caching is a well-known problem where we have a local cache of a constrained capacity, K, and at each time slot, this cache is receiving some requests or some files from a catalog N. And every time that a content is missing from the cache has to retrieve the file from a remote server, paying something in terms of cost that can be seen as the latency that we are going to experience every time we have to go to the remote server. And in particular, in this case, we are taking into account the possibility to have access to some predictions coming from, for example, the machine learning models about the request in the near future for the next time slot, let's say. So in this case, the object is that given the state of the cache xt, which is the set of files that are currently stored in the cache, the request that we receive at the time slot t, and the prediction for the next time slot t plus 1. We have to compute the next cache state in order to minimize the average miss ratio. Because if we minimize the average miss ratio, in some way we minimize the number of times that we go to the remote server. The challenge here is that, yes.
Are you going to edit from the cache based on prediction? So basically, you decide to replace something in the cache without having accurate request.
It depends. Yeah.
Yeah. The question was, are you evicting from the cache based on predictions, like you would in based on request from?
But it cannot. Yeah. And so basically, in this setting, in online cache, usually we have no assumption on the request. And mathematically, we model it like an adversary setting, where basically we are playing against an adversary with objectives to deteriorate the performance of the cache. And the state of the art, basically, all the algorithms that are trying to include this prediction, to take advantage of this prediction for deciding the next state for the cache, basically foreseen expensive operations, hindering the possibility of using this online gradient-based method in practice. So, first of all, we cast this problem into a line optimization problem, where basically each time slot we have a function that is proportional to the importance of each file, the number of requests that each file receives at each time slot, and proportional to the missing part of the file in the cache. So now, since we have we are in an adversary setting, it doesn't make sense to evaluate at each time slot whatever solution I gave to the adversary. So what usually we do is that we evaluate the algorithm, the performance of any algorithm, to a time horizon of length. And so we define to verify the performance of this method, we define a performance method that we call the regress. That's basically the superior of the difference between the cumulative cost to the time slot achieved by our solution and the cumulative cost achieved by the optimal static solution in outside. That is a solution that has access to all the time horizon. Okay. So let's see what are basically, okay, in this case, what I would like to say is that the desired solution in this setting of regress is to have a solution that has a sublinear regress in the length of the time horizon, because in this way, as t goes to infinity, the regress vanishes. And so we say that the algorithm has lost the desirable property for the algorithm. So, as I was saying, including such prediction is computationally expensive, because basically, in order to embed this prediction in the decision process, all the algorithms are based on the forward regularized feeder approach. Basically, in the forward regularized feeder, we are going to minimize the cumulative cost until time t to decide the state of time t plus 1, plus the function that we are forecasting to infer given the prediction, plus the regularization term. But this algorithm has a computationally expensive operation that is square in the size of the catalog. And this expensive operation is the projection into the complex sequence that is backend, which is the set of all the physical vectors that can represent a physical cache state. And furthermore, all these algorithms assume that the cache is updated at each new request. So at each time slot, we receive just one request. This means that we should perform this computationally expensive operation at each new single request that arrives. So the idea is to collect a batch of requests before updating the cache. In this way, we can amortize the updating cost. And so, in this moment, at each time slot, we have a set of R requests. We propose an algorithm that has coordinated caching, where basically the regularizer decompose over the coordinates. In this way, basically the regularizer, as soon as there are good predictions, follows the good prediction, because it depends on the prediction. We proved that this algorithm is a no-regret algorithm, and in particular, basically, we have zero regret with perfect prediction, because we have perfect prediction. But we have some linear regret even in the case of inference. So now, this solution, we experimentally test this solution. I have to okay. It's okay. It's a new style. And so basically, we tested this algorithm experimentally on a real dataset from Akamai with 20,000 requests and for 1,000 contents. And basically, first of all, we can see that this algorithm is robust even in presence of not so accurate predictions. And another thing is that obviously, if we increase the batch size, the average miss ratio decreases. But at least we have a reasonable batch size for which this algorithm outperforms the most implemented classical solution. So this means that this kind of algorithm can be also implemented in practice. So now, yes. Oh, sorry.
Are you assuming that? Yes. Are you assuming that the requests are stationary, so the distribution of requests comes always through the same distribution? And how does this impact, if it's not stationary, the speed at which the distribution that creates a request changes? How can this impact the optimal batch size? Yeah.
Thank you for the questions. So basically, no, we are not assuming that the requests are static because, as I said, we are in an adversary setting. So from the model point of view, we don't have any assumption of this. But experimentally, okay, if we have a static distribution, like let's take a zip distribution, okay, we know that LFU represents the optimum, okay. In this case, but for this I chose to represent these requests because they are real requests and they are not properly static. Okay, so I don't know if I answered the question.
How long is the part of the question? It's 1 hour or it's?
No, it was several hours. I don't remember the exact number, but it was
2 hours when it's still static.
Yes.
It's 3 months.
No, it was like something about weeks. But I think that all the traces were regarding 1 day for each content that it has been observed. But the whole dataset was about 1 week, I think. Yes. Did I answer the question? Okay. Thank you. So now I will move to the third work, basically, where I would like to see how these machine learning models work in order to understand what are the challenges when you work with these machine learning models. And in particular, I worked on a use case where, okay, you want to train a machine learning model, but you have a privacy constraint, okay? So basically, you have a set of clients and you want to learn a model from these clients, where each client has its own dataset. And you want to learn a global model, but these users cannot share their data set, okay? So we need to apply a distributed method to train the model, basically. And so this is an optimization problem because basically we have to solve this optimization problem to minimize a certain function that is the weighted sum of all the local function of each client, where each local function depends on a certain loss that is specified for each client. And basically, the typical solution is the federated learning, okay, which has been proposed by McMahon in 2017. But here we study a specific case of this federated learning. We study the case where we have heterogeneous availability of the clients, okay? So in order to explain better the question is that at each training period, basically the federated learning algorithm samples some clients from a given population. But in the case of large population like Google, for example, we can assume that each client is a sample at most once over all the training period because we have so many clients to choose from. But and so at each time slot we sample some clients, but in the small population this doesn't happen. In small population, each client can participate more than one time at the training phase. And furthermore, we have some problems of availability because if we are in a constraint where, for example, the battery of my device is very low, so the device is turned off, and so it won't participate anymore. So we have some correlation over the time. We have the temporal correlation of clients over the training period. And so the objective of this work is to study the convergence of federated learning algorithms when this happens. And the challenge is that basically correlation negatively affects the machine learning training. In particular, it slows down the convergence of the model. And in the state of the art, there is no convergence analysis for this case. So basically what we have done is that, okay, we can correct this. First of all, we provide the first convergence analysis for this case. And basically we bound the convergence, that is how far we are from the optimum, within two terms, an error about the optimization and an error about the bias model. Because basically this correlation, we proved that, okay, we can correct this slow convergence, but with the cost of convergence to a bias function, a bias model, which is a model that is far from the target objective. And basically, in order to minimize this convergence bound, we have to solve a convex problem, which is the one on the right. But basically, we can solve basically this problem with all the parameters, but there are some parameters that are difficult to tune. Okay, so we can solve, but sometimes the practical solution doesn't have any meaning. So, but at least the solution of this problem suggests us some guidelines to act on the client sampling and the aggregation strategies of the federated learning algorithm. And basically, the first guideline is that the first two guidelines is regarding how to accelerate the convergence speed. And this, we can do this by excluding clients with low availability. Here, sorry, the pi key is the availability of each client, because we model the client availability through affinity state Markov chains. And then we can exclude the clients with large correlation with this lambda pk is the largest second eigenvalue of the probability transition matrix of this Markov chain. And then in order to correct the bias of the model we are converging to, basically we can assign aggregation weights that are inversionally proportional to the availability of the client. So this method proved to be very effective, both in the convergence and higher accuracy, because we proved that basically we can balance this trade-off between a biased and the correlation and the convergence speed by just sampling strategy based on the availability and correlation of the clients. We performed an experiment both on synthetic and real dataset, and we can see that our algorithm that is called CAFED can achieve a better, higher accuracy and a better convergence rate. And I want to highlight that excluding clients also reduces the overall training cost, both in terms of computation and communication, because if you exclude more, you have to do less computation and communication. So the takeaways from these two works is that the first thing is that, okay, these machine learning models show an improvement of the application performance. For example, in the caching example, we have about 7% with respect to the classical approach. But basically, in the state of the art, is not taking into account the coordination between the predictions and the caching system. So they should be coordinated, these two aspects. And the third one is that, as I should know, is that performance of machine learning models are significantly influenced by exogenous factors like client's availability or network losses, if you want, failures in the network that are very common in a scenario like edge computing that we were talking about before. And so, what are the significant differences introduced by this machine learning model? This is consists of what I am currently doing and what I would like to investigate in the near future. Basically, okay, once we train these machine learning models are trained usually offline with an exponential number of possible configurations that are given by the hyperparameters that you are choosing to tune your architecture and so on, and the selected features. And at the end of this training phase, we are ending up with an inference model that is characterized basically by its accuracy at the moment of training and the size in terms of resource occupancy. So if we want to embed the inference model, these machine learning models, for example, into an application where it receives some data that are processed by other application components to give some, for example, predictions about this data, there are some difference in the behavior with respect to classical application that we were talking before. The first one is that basically this prediction contain errors depending on the accuracy of the model that we chose to perform the inference task. And this represents a completely different, a significant difference with respect to classical application, because now the behavior and the performance of the application doesn't depend just on the possibility of guarantees, the SLAs, the service level agreements. Okay, now the performance of the application depends also on the quality of the model that you've chosen to perform the inference task. The second difference is that basically for each inference task, we can choose different models with different configuration, and each configuration has its own levels of accuracy and size in terms, for example, this is a paper from Andrea also that shows some example of the YOLO applications. And this introduces a new level of complexity in the exploration of the solution space, because we have to dig on which variants of the model we have to choose also. And usually we are, as the table report, we are assuming that the bigger is the model, the more accurate it is. And the third one is that the actual performance of these machine learning models are influenced by exogenous factors in the training, as we saw before, but also during the inference. Because, example, for the concept drift, there are cases where basically the distribution of data that the model is currently seeing is different from the distribution of data this model has been trained on. And this can happen. Another exogenous factor can be also data loss, because if we don't have any data, there is nothing to infer. So this difference constitutes basically the skeleton of what I call the semantic requirements compared to the syntactic. Because if we come back to the analogy of writing code or writing a sentence, a semantic error is very hard to detect with respect to the compared to the syntactic requirements. So, given these new challenges, the orchestration should be revised, okay? Because, okay, we have, as before, we have constraints from the infrastructure side, we have requirements, the syntactic requirements, and then we have basically, for each inference model, apart from all the other components, we have to decide which model, which configuration, where to place in the network, and when to reconfigure as the network condition changes, and when we detect some exogenous factor or some data drift that is not trivial to detect. And so from the deployment point of view, this represents a new complexity level, okay, because we have different configuration for the model, and we have also to coordinate with the other application components. And from the management perspective, we have other challenges because we have, for example, the trade-off, if we assume that we have detected the concept drift, a data drift, for example, there are trade-offs like what is better, to replace the current model with a more accurate one, or is better to retrain the model? But okay, the retrain opens another Pandora's box, because then the question is, how can we retrain this? Do we have privacy constraints, or can do it in a centralized way, and so on? And sometimes the retrain depends also on the levels of accuracy that the application is requesting, because, for example, if we are in a very constrained environment, we can also decide to retrain with using like early exiting methods, where basically we stop the training at a certain level when we reach the desired accuracy levels, for example. I want to highlight that the state of the art is mostly focused on how to improve the performance on the training phase. And there is less research on how to handle the inference model once they have been trained. So basically, this has a significant impact on different use cases, this orchestration, on video analytics at the edge, on network caching, as I showed, on energy efficiency in networks. If we think about large language models or deep learning models, it's not so sustainable to put these models in like a tiny energy constrained device. So the orchestration could be beneficial in this case. And another use case where I'm currently working on is traffic monitoring. And I will show you some sketch of our preliminary result. So basically, this is a work with Francesco Bronzino I'm doing currently. And basically, is about traffic monitoring for video streaming quality inference. So we know that, okay, the service provider needs, as I told you before, is to ensure the application's requirements to perform some network management operation like traffic engineering or traffic shaping. And basically, why video streaming? Because video streaming represents 65% of all the internet traffic nowadays. And the question is, what about if we want to, the network operator wants to look at some metrics like video resolution? These are more explicit metrics, more representative metrics of the quality of the video that each user is receiving with their applications. But there is a problem, because nowadays the diffusion of an encryption protocol, this makes the traffic more opaque and hard to observe directly. And it's impossible to infer these metrics just looking at classical measurable metrics such as throughput, for example, or delay. But fortunately, has been shown that if we relies on this machine learning, we can infer such metrics. Now, how can we monitor the network traffic with this inference model? Basically, we inject the raw traffic into a pipeline that consists basically on some components. One of these is feature extractor that reduce significantly the traffic that is injected in the pipeline to extract the features that should be fed into the inference model. And at the end, we have the predictions on the quality metrics. But now we have to deploy these pipelines over the network, okay? We don't touch any, we don't interfere with the quality of the video that the users are receiving. We are just observing the traffic, but we have to deploy these machine learning pipelines to maximize the average accuracy that we obtain on this, on the traffic, basically. And the challenge is that, as before, we have different configurations for the inference model as before. And another challenge is to coordinate, because the feature extractor and the inference model are related. So the placement and the deployment should be taken into account also the feature extractor software components. And this problem is NPR, okay? And basically, the state of the art makes no distinction between these two components, but we will show that this distinction is beneficial, both in terms of accuracy and resources. So since the problem is NPR, basically we propose a heuristic solution that is based on the relaxation term. We formulate the problem as an integer linear programming problem, but we relaxed with so it becomes a linear programming problem, and we rounded this problem. And we can show that decoupling these two the inference model and the feature extractor is beneficial because it's more flexible, and it achieve 30% more higher accuracy with respect to the state of the art. And another thing that we can observe is that it's not true that to have higher accuracy, we have to observe more, but we can observe less with higher accuracy. So the research saying this, the research direction I would like to take in the orchestration machine learning based application now is basically divided in two directions that are dictated by the challenges that are included in this orchestration. The first one is the scalability. So the ability of these orchestration strategies and the algorithm to scale as the increase, as the size of the infrastructure, the size of application increases. And the second one is the adaptability. So the ability of these algorithms to adapt to exogenous factor or dynamic changes in the network and in the distribution of data that these models are receiving. And for all these challenges, I foresee to apply the methods I learned during these years. So, in order to conclude, this is a list of collaboration that is still active and they help me every time I need. And this is a list of selected publication. And I would like to conclude with a take-home that says, okay, these orchestration strategies are crucial in guaranteeing the main objective of the involved stakeholders, whether we have an application owner or we have a service provider. And the introduction of machine learning into this application is a game changer. And for this, we have to revise the orchestration strategies of the applications. And this has also a significant impact on different use cases I showed. So with this, I concluded the talk. Thank you for your attention, and I will be happy to answer any questions from you.
There are no questions. I have some.
I give you the mic.
Yeah, maybe they are too specific, but in general, when you in page 17, for instance, no, you want to evaluate your approach. So you evaluate in specific, specific conditions. Means you have a simulation, you input a simulation in which you give as input your Markov chains. These are these users that sometimes are available, sometimes are not. So you assume you know the availability because you impose that. And then under this big assumption that you know the availability, that you created your users, then you show that you can optimize things. So what happens instead, if you are not God and you didn't create the users are, and you don't know their availability when they come into the system, and you know nothing about them. So how can you adapt things to that case?
Thank you for the question. So, yes, okay, for the simulation, in some ways, you have to simulate the coming and go of the users, right? So we simulated like two different disjoint processes, okay? So the Markov chain is running and my algorithms of federated learning is running in parallel. So this is in some ways, the algorithm is not aware of the availability of the users in this way, because are two parallel processes, basically, in the simulation I'm talking.
But you did the script client based on the availability?
Yes, but sorry, this is a good question. Based on the historical availability that we've seen so far.
Not
Yes.
based on the
Yes,
theoretical
yes, but this was just for the analysis. Yes, sorry. This okay, in the analysis, okay, we selected, but in the simulation, in some ways, we don't have access to like the availability. This is the stationary probability of the Markov chain. So in the simulation, these are the guidelines that steer the design of the algorithm, but in the simulation is just like an estimation that we have of the availability. It's not, this is just for the analysis. Yes, thank you for this remark. Oh, can I throw it? Okay.
So I wanted to ask you about the last piece of work that you presented, traffic analysis. You mentioned running the pipeline, and I was wondering, where do you expect it to be run? Is it an ISP thing? Is it on a box? Is it some sort of, let's say, cloud thing? I did not really pick up from your description of the problem where you were. Okay.
So we, in this kind of, in this work, basically we are working on cellular networks. We envision to deploy the inference model, or this pipeline in base station, inside the base station, so inside the box of the base station that have some computational capabilities. Here, the problem is that the inference model doesn't have some, let's say, this high demand of resources. The problem for the resources, like in terms of CPU intensive, is the feature extractors, because it's what is cutting the raw traffic and is like a bottleneck, let's say. So basically, for the dataset, we are using a dataset from Orange. And no, so basically they are they is like a little bit noised, this dataset, because it's, I don't know if you know, is a NetMob 2023 dataset. Was a dataset that Orange gave for a challenge during this conference, and basically this dataset has the traffic volume of each base station across all the big cities in France. But in some case, we have to denormalize this traffic. And basically, we have, let's say, perform some cross-validation, because basically they give you, for example, they give you the incoming traffic of each base station, but they don't give you the position of the base station. So we had to cross two data sets. Another one is the how to say census data set of the city of Lyon. This was based on this. And but yes, basically it was just traffic, but for mobile. No, it was like more, the granularity was a little bit loose. It was just traffic volume that about the specific applications. These results are for Netflix applications. No, not for user. They are cumulative. Okay.
You understand the quality of typical users when you're looking at the complete kind of sub-level users into a single application.
Okay, so this is a good question. So basically, we basically from the traffic that we are looking at, we are making some assumption that says, okay, we know on average what is the size of a flow of Netflix, and so we can retrieve the number of flows and so on the number of users that are in each measurement. No, the quality, the ground truth is impossible to have because it's encrypted. But you have the quality according to the model that you choose. Not the quality, a prediction about the quality. Okay.
So you showed the performance of an algorithm who is meant to minimize regrets. So maybe an algorithm that is good at minimizing regret is very bad at improving practical performance, because you do actions for the worst case, but maybe this case is very far from the worst case. So do you compare in your graph, in your plot? I don't know if you have some comparison of how bad is the algorithm that is meant to protect from the worst case with respect to maybe some algorithm that optimizes for the average case.
Yes, indeed. Okay, in the state of the art, we have basically two metrics to choose from. One is the regret, and one is the it's called, I think, optimal ratio, something like this. But they are both of them are pessimistic metrics. But the optimal ratio was more pessimistic with respect to the regret. So for this reason, we chose to be. And so first of all, I agree with you that it's a pessimistic. And for the average case, basically, we compared against LFU and LRU, which are for two reasons. The first one is that they are good in practice, because beyond the fact that they are good practice, in practice they are very easy to implement. Okay, so but we compared against them also because in some cases where in the static case LFU, as I said before, as an optimal behavior, and in the case where we don't have a static distribution, LRU should be performed better than LFU. So for this reason, we show this. I don't know if I answered your question. Thank you. Thank you. Yes. I don't know if I have to. Here I can.
Maybe Christina also related to the question. So, Alberto is still there. You can still answer. You can still answer
Okay.
if he's there.
Alberto, can you hear me?
Yes, thanks. Yeah.
Okay. So I'm reading your questions. So about why splitting feature structure from inference is beneficial. Okay, yes. So it's beneficial because basically splitting these two aspects, you are more flexible in the deployment, basically, because with respect to the state of the art that they are assuming that the inference model and the feature structure are on the same place. This basically occupies some resources, so you can better exploit your resources in this way.
Okay, I understand. So it has nothing to do with the AI and the ML itself. It's really about the orchestration, in fact.
Yes, it's more related on the resource allocation side,
Okay.
let's say.
Okay.
Yes.
I thought there were a link with respect to the fact that you have multiple versions of the same model, and that there could be then multiple versions of feature extraction also.
In some ways to this is related, because basically what happens basically if you decouple these two, sometimes you can dedicate more resources to the inference model, and so to select the configuration with the highest accuracy. Okay.
Yeah.
Meanwhile, you can deploy the feature extractor on another node.
Yeah. Okay.
But if you constrain them to be together, basically you are penalize the inference model.
Yeah. Okay. No, it's fine. I got it. Okay. Yeah. Okay. Perfect. Thanks.
Thank you. Thank you for the question. I don't know if there are other questions. Okay. Okay. It was. I think I can close.